Bismillahirrahmanirrahim. Welcome in class of elementary number theory. In today's lecture, we are going to start a new chapter, chapter 2, Divisibility theory in the integers, from the book of David M. Burton. Today video, we will focus on a very important type of the number, that is the triangular number. The first two pages of this chapter are the literature review and some historical backgrounds of number theory. If you have interest in reading, you can read those pages by yourself. So the first exercise, the problem 2.1, consists on 11 questions. The first 9 questions are related to triangular number. So let us discuss how can we define the triangular number. Actually, a triangular number is a number that form an equilateral triangle uh, by arranging the dots. For example, we start from n is equal to 1. N is equal to 1 means there is a single dot here. When n is equal to 2, it shows the sum of the first two in positive integers, that is 1 plus 2. This is equal to 3. In this case, we will plot or arrange three dots such that they form an equilateral triangle like this. So these three dots form an equilateral triangle. The number of dots in each side are 2. When your n is equal to 3, the number of dots are given by sum of first three integers, 1 plus 2 plus 3, which is equal to 6. Now the number of dots along every side of equilateral triangle will be 3. This is first dot. These are 2, and now these are 3. You can count, these are total 6 dots. The very interesting thing is that if n is equal to 3, then this triangle has a 3 rows. In the first row, there is a 1 dot. In the second row, there is a 2 dots. In the third row, there are 3 dots. Similarly, when n is equal to 2, there are the 2 rows. In the first row, there is a 1 dot, and in the second row, there are 2 dots. In case for n is equal to 4, the number of dots are given by 1 plus 2 plus 3 plus 4, sum of the first 4 n natural numbers, that is simply given by 10. Now the equilateral triangle that we will make here consists on 4 rows. Something like this. This is the first row that consists on first 1 dot. In the second row, there are 2 dots. In the third row, there are 3 dots. And in the last row, there are the 4 dots. So continuing this process, every number that is sum of these dots is called a triangular number. So the sequence of triangular number is given by sequence of triangular number. Are given by 1, 1 plus 2, which is equal to 3, 1 plus 2 plus 3, which is equal to 4. Next one is 4 plus 3. Sorry, this is equal to 6. Sorry, 6 plus 4, that is equal to 10. The next one is 10 plus 5. In other words, 1, this is the sum of first 5 natural numbers. 1 plus 2 plus 3 plus 4 plus 5, which is given by 15. So continuing this process, the nth triangular number is simply nth triangular number is simply given by the sum of first n natural numbers. 1 plus 2 plus 3, 4, up to so on n. And the sum of the first n natural numbers, simply equal to n into n plus 1 over 2. And this number we will call, in incoming questions, this number is called the nth triangular number. This is the nth triangular number. Nth triangular number. And we will denote it by Tn is equal to n into n plus 1 over 2. So by using this nth triangular number, we can find the number of dots in any particular equilateral triangle. For example, if you are interested to find the number of dots in eighth equilateral triangle, the number of dots will be simple 8 into 8 plus 1 over 2, which is equal to 8 into 9 over 2. This is 36. So you will see in the exercise, in these 9 questions, you will observe very interesting properties, facts and observations related to triangular numbers. And particularly the question number 9 is one of the fascinating question of the exercise. So let us start from question number 1. Okay, let us start from the first part, question number 1a of problem 2.1. I have not written the complete statement of the question. The first few lines are related to the definition of triangular number that I have already discussed. In the first A part, we have to show that a number is triangular if and only if it is of the form n into n plus 1 over 2. We suppose x is any number formed by n dots. Then by definition of triangular number, x is equal to the sum of the first n natural numbers. So you will write, let x be a triangular number, and we will show that it is of this form. Then by definition, let x be a triangular number formed by n dots. Then by definition of triangular number, x can be written as 1 plus 2 plus 3 up to so on n. Now this sum is simply equal to n into n plus 1 over 2. The proof of the sum of first n natural number is given in question 1a, problem set 1.1. We have already proved in this problem that the sum of first and natural number is simply is equal to this. So when x is a triangular number, then it can be written simply in this form. Now suppose that okay, next, conversely we suppose that x is equal to, conversely suppose x is equal to n into n plus 1 over 2. Then again, by using this reference, this is simply equal to 1 plus 2 plus 3 up to so on n. So the first part is very simple. In the second part, we have to show that an integer n is triangular if and only if 8n plus 1 is a perfect square. In the B part, an integer n is triangular if and only if 8n plus 1 is a perfect square. If you have not its hard or soft form of this book, the link is available in the description box. You can download this book in soft form, as well as there are very helpful material in Google Drive available. In this question, we have to show that an integer is a triangular if 8n plus 1 is a perfect square. We suppose n is a triangular. Suppose n is a triangular number. Then by definition of triangular number, then for some integer m greater than or equal to 1, according to the first part, this n can be written as the sum of the first m natural number 1 plus 2 plus 3 up to so on m, which can be written as m into m plus 1 over 2. We suppose n is a triangular number, and we will show that 8n plus 1 is a perfect square. If n is a triangular, then it must be that there exists some integer m such that this n can be written as the sum of these first m natural numbers. Now we solve 8n plus 1. We show that 8n plus 1 is a perfect square. This implies 8n plus 1 is equal to, what is n? N is here m into m plus 1 over 2 plus 1. This is simply equal to 4m square into 4m plus 1, which is given by 2m plus 1 whole square. That is a perfect square. This is a perfect square. Conversely, we suppose that 8n plus 1 is a perfect square. Now n is a triangular number. Conversely, suppose 8n plus 1 is a perfect square. We show n is a triangular. N is a triangular number. Okay, if 8n plus 1 is a perfect square, we can write it as 8n plus 1 is equal to square of some integer k. If you see this number 8n plus 1 For all n greater than or equal to 1, the number 8n plus 1 is an odd integer. This is an odd integer. This is an odd integer. It means the right side, that is k square. K square is an odd integer. If k square is odd, implies k is odd. K is odd. Let k is equal to 2q plus 1, where q is any integer. So this number is an odd integer. Put k is equal to 2q plus 1 here. This becomes 8n plus 1 is equal to 2q plus 1 whole square. This is given by 4q square plus 1 plus 4q. 8n plus 1. Subtracting 1 on both sides, and the remaining, taking common 4q, we have q plus 1. Dividing by dividing by 8 on both sides, this gives us q into q plus 1 over 2, which is the form of a triangular number. If n is a triangular number, then it will always have the form of n into n plus 1 by 2. So this is the form of n into n plus 1 by 2, where n is a positive integer. Form of a triangular number. This is a form of triangular number. That completes the proof. The next one, in the C part, the sum of any two consecutive triangular number is a perfect square. Now we have to show that the sum of any two consecutive triangular number is a perfect square. In the C part, sum of any two consecutive triangular numbers is a perfect square. You can solve this question by two ways. Suppose x and y are the two consecutive integers, then x is equal to, suppose x is formed by the first n natural numbers, then x is equal to sum of first n natural numbers. As y is consecutive to x, then the number of the integers in y will be n plus 1. I again repeat, suppose when you see the sequence of triangular number, the first triangular number is 1, the second one is 1 plus 2, the third one is 1 plus 2 plus 3, the third triangular number is 1 plus 2 plus 3 plus 4, the fifth one is 1 plus 2 plus 3 plus 4 plus 5th. So every next triangular number is the sum of previous plus the value of n. In other words, the recursive relation, in form of recursive relation, you can write a triangular number in this form: an plus 1 is equal to an plus n, where n is greater than or equal to 1 and a1 is 1. So if x and y are the, simply if x and y are the consecutive triangular number, then and x has a n dots, then the number of dots in y will be n plus 1. simply. Now x is equal to simply this is equal to n into n plus 1 over 2, and y is equal to, y is the sum of first n plus 1 natural numbers. So this is equal to n plus 1 into n plus 2 divided by 2. By just simply replacing in this formula, that is the formula of sum of first n natural number, you can replace n by n plus 1. We can obtain the value of y. Now our target is to show that the sum of any two consecutive triangular number. Now we show that x plus y, the sum of these numbers, n into n plus 1 over 2 plus n plus 1 into n plus 2 over 2. This sum is a perfect square. Okay. Now this has a just simple calculation. By taking n plus 1 by 2 common, n plus 1 by 2, taking this factor common, the remaining is n plus n plus 2. Yes, sum of any two consecutive triangular numbers is a perfect square. Sum of, yes, perfect square. N plus 1 over 2, this is 2n plus 2. By taking common 2 from, this is equal to n plus 1 whole square, which is a perfect square. This is a perfect square that is required. So this is question number 1. C. In the question number 1D, if n is a triangular number, then show that 9n plus 1, 25n plus 3, 49 plus 6 are also triangular number. This result was introduced by Euler in 1775. This result says that D part, if n is triangular, then we have to show that 9n plus 1. The next number is 25n plus 3. And the next is 49 plus 6. 49n plus 6. These are all also triangular number. So the key point throughout the exercise is simple. A number n is called a triangular number if it can be written in this form. A number, any number x, y, z is called triangular number if it can be written in this form. N into n plus 1 by 2. Simple. This is the simple key idea. Suppose that n is a triangular number and the sum of the first m positive integers as n is triangular so for some m greater than equal to 1, this triangular number n can be written as m into m plus 1 over 2. Now we have to show that 9n plus 1 is also a triangular number. Here 9n plus 1, 9. What is the value of n? N is here m into m plus 1 by 2 plus 1. So by taking LCM, this is 9m square plus 9m plus 2 over 2. Yes. By making factorization here, this gives us 6m plus 3m plus 2 over 2. By taking 3m from here common, we have this is 3m plus 2 plus 1 3m plus 2 over 2, which is simply equal to 3m plus 1 into 3m plus 2 over 2. As m is any positive integer, then clearly 3m plus 1 is also a positive integer. So suppose let 3m plus 1 is equal to s. This implies 3m plus 2 is equal to s plus 1. So this form becomes s into s plus 1 over 2. So 9n plus 1 is equal to s into s plus 1 by 2. That is the form of n into n plus 1 by 2, which shows that the number 9n plus 1 is a triangular number whenever your n is a triangular. Similarly, you can prove easily 25n plus 3 and 49 plus 6 are also a triangular number. So this completes the question number 1. Next is also very interesting and very easy question. Question number 2. Okay, the next question is question number 2. The statement of the question is, if Tn denotes the nth triangular number, prove that in terms of binomial coefficient, Tn can be written as n plus 1 combination 2. So this is a very easy and simple question, but the purpose of the question is to represent the triangular number in form of binomial coefficient. So just by using formula of combination rule, this can be written as n plus 1 factorial over 2 into n plus 1 minus 2 factorial. Next we break the factorial, n plus 1 into n minus 1 factorial over 2 factorial, that is 2, and this is n minus 1 factorial. Cancelling the same factor, we have n into n plus 1 over 2. That is the definition of the triangular number. So now you can do question number first C, whose statement is the sum of any two consecutive triangular number is a perfect square. You can do this question by simply, this is my first number Tn, then the next consecutive number is Tn plus 1. This is equal to simple n plus 2 combination 2. Now by adding these two numbers, Tn plus 1, you can prove the answer is simply a perfect square. Next question number 3 is attributed to the Hindu mathematician Aryabhata. In this question, we have to derive the formula for the sum of triangular numbers. Question number 3. The sum of the first n triangular number T1, T2, T3 up to so on Tn is simply equal to n into n plus 1 into n plus 2 over 6, where n is greater than or equal to 1. To prove this question, uh, I will use the uh, binomial coefficient here. T1 is simply equal to, if we put n is equal to 1 here, this is equal to 2 combination 2. 2 combination 2. Similarly, 2 for n is equal to 2, we have 3 combination 2. So, the left side becomes 2 combination 2, 3 combination 2, 4 combination 2, up to so on. The last one is n plus 1 combination 2. Now, how we will sum these terms? In question number 5a of last chapter, problems 1.2, we have proved a result by mathematical induction that n combination 2 plus n combination 3, n combination 2, n combination, this is 2, 3, 4 combination 2, 5 combination 2, up to so on n combination 2. This is simply equal to n plus 1 combination 3. So according to this result, we can sum it. If the last number is n, this is increased by n plus 1. Now our last number is n plus 1. So this is simply equal to n plus 2 combination 3. Next we use the combination rule here and prove this. This is equal to n plus 2 n plus 1 into n over 3 factorial by just opening this and after cancelling some common factors, we have remained this, and 3 factorial is simply 6. That completes the proof. Question number 3. Next question number 4. In question number 4, the statement is proved that the square of any odd multiple of 3 is the difference of two triangular numbers. Specifically 9 into 2n plus 1 whole square, this is equal to t 9n plus 4 minus t 3n plus 1. We have to show that square of any odd multiple of 3, any odd multiple of 3 for all n greater than or equal to 1, the number 2n plus 1, this is an odd integer. Now, odd multiple of 3 means 3 into 2n plus 1. This is odd multiple of 3. Now, when you take square of this number, 3 into 2n plus 1 whole square, this is equal to 9 into 2n plus 1 whole square. We have to show that this can be written as a difference of two triangular numbers, specifically these two. So, how we will solve this? We will solve this side of triangular number. We will apply the definition of triangular number on the right side, and after some calculation we will reach at this result. For example, the first triangular number t 9n plus 4 is simply equal to 9n plus 4 into 9n plus 5 over 2. By using the formula, triangular number is simply equal to n into n plus 1 over 2. Your triangular number is simply equal to n into n plus 1 over 2. Now, if the subscript is 9n plus 4, so we write it here 9n plus 4, and by increasing 1 unit, we have 9n plus 5. over 2. Similarly, t3n plus 1, this is simply equal to 3n plus 1 into 3n plus 2 minus over 2. Now subtracting these two numbers, and after solving, we can find this result. The next question number 5 is a very interesting question, and actually this question is a research based question. In the question number 5, question number 5, in the sequence of triangular numbers, find the following. Firstly, we write sequence of triangular number as sequence of triangular numbers is given by the first number. Now this is 1, the second one is 1 plus 2, that is 3, the third one is 1 plus 2 plus 3, that is 6, the next one is 6 plus 4, that is 10, 10 plus 5, this is 15, next one is 21, 21 plus 7, this is 28, 28 plus 8, 36, 36 plus 9, 45, 45 plus 10, 55, next one is 55 plus 11, 66, up to so on. Now the first question. In the sequence of triangular number, find the following. Two triangular numbers, you have to find two triangular number whose sum and difference are also triangular number. You have to find two triangular numbers whose sum and difference is also a triangular number. From this sequence, you can easily find the two numbers whose sum is a triangular number and whose difference is also a triangular number. Mean to say, find the two numbers among these. Whenever you sum those numbers, the result is among these numbers. So these are the fifth number T5, which is equal to 15, and the next one is T6, which is equal to 21. You can observe that their sum T5 plus T6, 15 plus 21, this is equal to 36, and which is equal to 5, 6, 7, 8, T8. Similarly, if you subtract these two numbers, T6 minus T5, 21 minus 15, this is equal to 6. That is the third triangular number, T3. So in this sense, this question is easy. But I said that this question is actually a research-based question. How this question is research-based? In general, if we have to find other numbers, other pairs of triangular number whose sum and difference is also a triangular number, then how will you find? We suppose TA and TB are the two triangular numbers such that their sum is again equal to a third triangular number TX, and their difference is again equal to a third triangular number TY. Now this gives us actually two equations, system of equations that are called linear Diophantine, non-linear Diophantine equations actually, that we will discuss in incoming lectures inshallah. But this is not easy to solve these two equations unless we assume some assumptions So in this sense, I said that these questions are actually this question is actually a research based question. Otherwise you can find easily the two numbers from this sequence whose sum and difference is a third number. And it might be possible that there exist many other pairs whose sum or difference is also a third triangular number, and we will discuss this scenario in question number 9. In that question, you will see the sum of a two triangular number is again a third triangular number under some condition. Okay, it's B part. In the B part, uh, you have to find three successive triangular number whose product is a perfect square. Number should be successive. Successive means consecutive. Successive. But now product is a perfect square. Product is a perfect square. Can you find from here? Yes. 6, 10, 15. If you see, their product is 900, which is 30 square. They are perfect square. So from this sequence, the three consecutive triangular number whose product is a perfect square are 6, 10, and 15. And similarly, in case of general, how we will solve this? Suppose Tn, Tn plus 1, Tn plus 2. These are the three consecutive or successive triangular numbers. Now, this is simply n into n plus 1 over 2. Tn plus 1 is simply n plus 1 into n plus 2 over 2, and Tn plus 2 is equal to n plus 2 into n plus 3 over 2. This should be equal to a perfect square. Suppose this is equal to k square. K is a positive integer. Now, this can be written as n into n plus 1 whole square, n plus 2 whole square into n plus 3. We write this, and this is 2 to the 4. Combine that 4 with k square, we have 2k whole square. Now, this side will be a perfect square if this number is perfect square. N into n plus 3 over 2 is a perfect square. So by using trial and error method, you can find the different values of n for which this number is a perfect square. For example, if you put here n is equal to 3, put n is equal to n is equal to 3. Okay, n is equal to 3. This becomes 3 into 6 over 3, that is equal to 9. That is a perfect square. For n is equal to 3, your number is T3, T4, T5. These are the three successive numbers for n is equal to 3, and these are the same: third, 4, and fifth number. Similarly, you can find other values of n. You can put other values of n and find the result for which value of n is the result is a perfect square. It just depends on this factor. So in this sense, I said that this question is a research based question. Similarly, in the C, now we have to find the three successive triangular number whose sum is a perfect square. Whose sum is a perfect square? Now sum is a perfect square. So simply these numbers 15, 20, 21 and 28. The sum of these three numbers is 8, 9, 5. 64. Yes, the sum of these three numbers is a 64. That is a perfect square. Okay. The next one, question number 6, is also very interesting question. Yes. Okay. Next I am solving question number 8. Question number 6 and 7 are your assignment. I hope you can do this question very easily. Still you find any difficulty, the solution of this question, the link of the solution of this question is available in the description box. In the question number 8, we have to prove that the sum of the reciprocals of the first n triangular number is less than 2. That is, if you see the denominator, this is this is the first triangular number, 3 this is the second triangular number, 6 this is the third triangular number, 4 triangular number, up to so on nth triangular number. The sum of the reciprocal of these n triangular number is always less than 2. We will use here a very simple concept here. Each term of this sum can be written as each term of this sum can be written as 1 over k into k plus 1 over 2 for any k greater than or equal to 1, because you know the every triangular number is always of this form. Further, this can be written as 2 over k into k plus 1, and this is equal to 1 over k minus 1 over k plus 1. So this form is equal to this. So when you put k is equal to 1 here, we can obtain the first term. For example, if you put here k is equal to 1, this gives us 2 into 1 over 1 minus 1 over 2. This is 2 into 1 minus half. This is half, that is equal to 1. So the first number, that is 1 over 1, can be written as. So now I am writing all of the number in this form. This implies 1 over 1, 1 over 3, 1 over 6, 1 over 10, up to so on 1 over tn. These all numbers can be written as. The first number is 2 into 1 over 1 minus 1 by 2. The second number 2 into 1 by 2 minus 1 by 3. You can verify this here. The LCM is 6, 3 minus 2, 1 by 6 into 2, that is 1 by 3. 2 into 1 by 3 minus 1 by 4 plus 2 into 1 by 4 minus 1 by 5 up to so on. The last number is 1 over n minus 1 over n plus 1. Now by taking 2 common and expanding these brackets, we have left only two terms, this one and the last term. This becomes 1 minus 1 over n plus 1. As n is a positive integer, this implies n plus 1 will also greater than 0. This shows its reciprocal is also greater than 0. But this number 1 minus 1 over n plus 1, 1 minus 1 over n plus 1, this is always less than 1 because this quantity is positive. So when you subtract any positive quantity from 1, the answer is always less than 1. Multiply 2 on both sides, this gives answer less than 2. That is required to prove. Now I am discussing the very important, very interesting, very fascinating question of the exercise. Question number 9. It might be possible that you have a curiosity that when does it possible the sum of the two triangular number is equal to the third one. The third one is also a triangular number. When does it possible? This all situation is clear in question number 9. In question number 9, we have to establish an identity in which the sum of the two triangular number is always equal to the third one. Although this is not a very easy task to investigate this identity, but as in the context of solution, this is very easy. We have given some certain conditions. We will use that conditions and show that this identity hold. So what is the question number 9? Question number 9. Okay. Well, the statement of question number 9 is 9a. Establish the identity Tx is equal to Ty plus Tz, where this is important, where x is n plus n into n plus 3 over 2 plus 1, where y is equal to n plus 1, and where z is equal to n into n plus 3 over 2, and n is greater than or equal to 1, thereby proving that there are infinitely many triangular numbers that are sum of the two other such numbers. So in the solution point of view, we just have to show the left hand side is equal to the right hand side. What is Tx? Tx, my x is n into n plus 3 over 2 plus 1. Using the definition of triangular number, you know, a number is called triangular if it can be written in this form, n into n plus 1 over 2. So this should be n into n plus 3 over 2 plus 1 into n plus 3 over 2 plus 1 plus 1. If you have a confusion, I have just replaced n by n into n plus 3 by 2 plus 1 in this formula. Okay, this is simply is equal to n into n plus 3 over 2 plus 1, n into n plus 3 over 2 plus 2. We will not solve further this side. Next, right hand side. The right hand side is Ty plus Tz. What is y? Y is here n plus 1. And what is z? Z T n into n plus 3 over 2. Okay. Now to find Tn plus 1, this term, we just replace n is equal to n plus 1 in this formula. So this gives us Tn plus 1. This is n plus 1 into n plus 2 over 2. This is the value of Tn plus 1. Next plus n into n plus 3 over 2 into n plus 3 over 2 plus 1 over 2. Here I think I have a mistake here. Yes. There is a 1 by 2 here. This one. Okay. After multiply these two factors, we have n square plus 3n plus 2, and after separating 2 we have plus 1 by 2 into n plus 3 over 2 n into n plus 3 over 2 plus 1. This is n into n plus 3 over 2 plus 1. Okay. If we take common this number from these two, we have 1 plus 1 by 2 into n plus 3 over 2. That is same as this. Lastly, taking common 1 by 2 from this, we have 1 by 2 n into n plus 3 by 2 plus 1, 2 plus n into n plus 3 over 2. Hence, left hand side is equal to the right hand side. So next we discuss its B part, the last question of today lecture. Okay, this is our last question of today lecture, and now I am going to discuss the most important segment of today lecture that I have been waiting for a long time. Question number 9b. In question number 9b, we have to find 3 examples of a triangular number that are sum of the other triangular numbers. In this question, you will see under what condition, when does it possible that the sum of the two numbers is equal to a third number, and third number is also a triangular number. But now we have to find just an examples. For n is equal to 1, when n is equal to 1, in question number 9a, you have established an identity tx is equal to ty plus tz. The sum of two triangular number is equal to third triangular if x is equal to, this is x is equal to n into n plus 3 over 2 plus 1. When you put n is equal to 1 here, this is 4 by 2. 4 by 2 means 2 plus 1. This is 3. So value of x is 3. Value of y. Your y is n plus 1. N plus 1 means this is 2. When you put n is equal to 1 here. The last one is z. When you put n is equal to 1 here, this gives us 1 plus 3, 4. 4 by 2, that is 2. Now, you find the first triangular number, that is tx. Tx means, what is the value of x? X is 3 here. T3. T3 is simply 3 into 3 plus 1 over 2 by the formula n into n plus 1 by 2. This is equal to 3 4 the 12, 12 by 2, 6. This is tx. Ty. What is ty? T2. T2 means 2 into 3 over 2, this is equal to 3. Tz. What is z? Your z is 2. Your z is also 2, which is equal to 3. So you can verify that here sum of these two triangular number ty plus tz is equal to the third triangular number. Ty is equal to 3, tz is also 3, and tx, x is 6. 3 plus 3 is equal to 6. This is the first example. Similarly, you can find another example. For n is equal to 2, if you put n is equal to 2 in x, y, z, your axis, when you put n is equal to 2 here, n is equal to 2 here, this will become 5. 5 plus 1, 6. X is equal to 6 here. Your y is n plus 1. 2 plus 1, this is equal to 3. And your z is equal to simple 5. Now, this gives tx. Tx means t6. T6 means 6 into 7 over 2. This is equal to 21. Ty. Matlab T3. T3 means 3 into 4. This is equal to 6. And lastly, Tz. Tz means T5. T5 means 5 into 6 over 2. This is equal to 15. Again, you can observe that 21 is equal to 15 plus 6. That is, Tx is equal to Ty plus Tz. Similarly, you can find the third example also. For n is equal to 3, you can again find the values of x, y, z, and you will find that this identity hold. So you can find the infinite number of triangular pairs such that the sum of the two triangular number is again a third triangular numbers. So I hope today lecture is very interesting and very helpful for you. In the next lecture, we will discuss another type of a number that is known as pentagonal number. But this type has only two questions in the exercise, question number 10 and question number 11, that we will discuss inshallah in the next lecture. So if you find this lecture are helpful for you, kindly like, share. So see you in the next lecture. Take care. Allah Hafiz.